An important aspect of multivariable integral calculus, especially later on in the term when we're doing line integrals, is parameterizing curves. So I just want to review a couple examples of this. The first example is just to parameterize a circle. So here's a circle of radius 2 with center 4, 5. Now I specifically want a clockwise parameterization of this circle, and I'm also specifying a starting point. So there's a couple things we have to keep in mind, but this is roughly just a review of how to parameterize a circle. So let me draw a picture really quick here. Okay, so here's the circle that we're looking for. It's got a center 4, 5. It has a radius of 2. And like I specified in the problem, I specifically want to start up here and travel clockwise. So I want to travel this way. Now a good starting point here is to go back and think about the usual parameterization of the unit circle. And in particular, the usual counterclockwise parameterization of the unit circle. The typical way that we do that is with cosine and sine as the x and y component, respectively. Now, one issue with this, or there's a couple issues with this, which is the usual parameterization of the unit circle is a counterclockwise parameterization. You can see this either by plugging in some points here, or, for example, taking the derivative and looking at the tangent vectors. The other issue is that in the circle that we care about, I want to start up here, and the usual parameterization starts on the right-hand side. So we have a couple things to keep in mind, but this is, in any case, a good starting spot. Okay, so how can we fix these issues? Well, first of all, we need to take care of the center and we need to take care of the radius. If I start with a parameterization like this, I can adjust the center by just adjusting the x and y components, respectively. In particular, I want to take this whole picture and shift it to the right 4 units and up 5 units. So I could start by, what if my x component looks like 4 plus something, and the y component looks like 5 plus something? Like I said, essentially what this does is it just takes whatever picture we're starting with here, shifts it to the right 4 units, and up 5 units. Now the other thing that we need to take care of is the radius. The radius of this parameterization here, of this circle, is 1. We want our circle to have a radius 2. Again, starting from this picture, I can change the radius by just multiplying each component by a number. So like if I put a little 3 here and a little 3 here, that would scale each component by 3, and it would give us a circle of radius 3. So to get a circle of radius 2, I'm going to want a 2 times something and a 2 times something. The last thing we need to do is we need to figure out what kind of trig functions we want to write here to accomplish the correct starting spot as well as the correct direction. Like I was talking about here, if we were to write cosine and sine here, we would get the circle of radius 2 with the correct center, but it would be starting at the point 6, 5, and it would travel that way. So one way that we could play around with this is we could say, well, what if we switch sine and cosine? So for example, what if I write 2 sine of t here and 2 cosine t here? Let's check to see if this works. First of all, when r is 0, when t is 0, what point are we at? Well, sine of 0 is 0, so the x component is 4. And cosine of 0 is 1, so the y component is 5 plus 2, which is 7. And that's exactly what we wanted up here. So I guess we got a little lucky by switching sine and cosine. We have arrived at the correct starting spot. The last thing that we need to check is that if the direction is correct. Now, Because we've used sine and cosine, it takes 2 pi units of t to travel once around the circle. So one way we could check this is we could just check that when t is pi over 2, what point are we at? Well, sine of pi over 2 is 1. So the x component is 4 plus 2, which is 6. And let's see, cosine of pi over 2 is 0. So the y component is 5 plus 0, which is 5. And that point, where is this on the circle? That's right here. This is the point 6, 5. So this indicates that we're traveling in the correct direction, which is clockwise. And there you go. So there's our parameterization, and we're done. Now, a quick remark, like I said, I just kind of got lucky. I said, oh, let me switch sine and cosine and see if that works, and it did. And a good question is, Joe, what if that doesn't work? Like, what else can I do? You know, you can play around with switching sine and cosine. You could change this plus and this plus to a minus. That would effectively change starting positions and could change the direction as well. So those are the kind of parameters that you can tinker around with. Like I said, the other way that we can check that the direction is correct, here I just kind of plugged in 2 points, but another way that you could do this is you could look at tangent vectors. Maybe let me do that really quickly up here. With our parameterization, what is r prime of t? The derivative here is going to be 2 cosine t. The derivative here is going to be negative 2 sine t. And so, for example, when time is 0, what does this vector look like? Cosine of 0 is 1, so this is the vector 2, and then sine of 0 is 0, so this is the vector 2, 0. So that tells us that the tangent vector at time 0 is 2, 0. Let me draw that vector in here, and this will show that the direction is in fact correct. At time 0, earlier we determined that we were at the point 4, 7. The vector 2, 0, starting at the point 4, 7, goes 2 units to the right and no units up. So that would look something like that. Again, r prime here, this is the tangent vector at this time, and it indicates the direction of travel. So this confirms that we're traveling in the correct direction. There you go. Okay, next up is another parameterization problem, but this one's a little different. I'm giving us 2 surfaces. They intersect in some curve, and I want to parameterize the intersection of that curve. One of the surfaces is x squared plus 2y squared equals 4. The other one is z minus x squared plus y cubed equals 1. Okay. Now, this is a good problem to demonstrate a theme of multivariable calculus, which is going to come up a lot throughout the quarter. And that is that there's a delicate balance between relying on geometry and being able to visualize what's happening, and then just trusting the equations that you're given, trusting the algebra and trusting the formulas. Because on the one hand, and I'll try to do this, we could try to visualize these surfaces and we could try to visualize what the intersection will look like. That may help us, it may not. But in general, this kind of thing is pretty difficult, and usually you can get away with just trusting the equations and going from there. In any case, let me try to draw these pictures and I'll convince you what they look like. So the first surface is x squared plus 2y squared equals 4. If I gave you this equation in the xy plane, you would tell me it's an ellipse. And that's correct. Now, this is a surface in 3 dimensions, so roughly what happens is we just have this ellipse in the xy plane. There's no restriction on z, so it just travels up and down forever, and we get this elliptical cylinder. Let me attempt to draw that. Okay, there's my elliptical cylinder. Goes up and down forever and ever. And then we have this other surface given by z minus x squared plus y cubed equals 1. I don't know what that looks like, but I do know that I can write this surface as the graph of a function of x and y. So maybe the next thing I'll remark, and this will be important in a second, is that the second surface we can rewrite as z equals, move all these other variables over here, and we'll get 1 plus x squared minus y cubed. Now, I don't really know what this actually looks like. If you held me up against a wall and told me to figure it out, I could do it by looking at traces and stuff like that, but it's not really necessary. I just know that it's the graph of a two-variable function, which means it's going to look like some graphical blob over the xy plane. So let me draw a heuristic picture for that. Okay, I don't know if this makes sense at all, but here's my drawing of the other surface in green. And the point is that we've got some cylinder and we've got some blob and they intersect. And their curve of intersection can be something in orange. So maybe we get something like that. Who knows? Okay, and then the orange thing is what we're trying to parameterize. Now, like I said, we have a beautiful picture, and maybe it helps us contextualize what we're doing, but did this actually help us figure out anything? Maybe, maybe not. What I was talking about earlier is that in general, it's a good idea to just trust the equations and go from there. In particular, a good strategy for parameterizing intersections of surfaces is use one of the equations to determine two of your components. So earlier I talked about how this equation, that made me think of an ellipse in the xy plane. And then I think, I know how to parameterize an ellipse. So what I'm going to do is I'll use this equation, pretend it's just an ellipse, write down what my x and y functions are, and then this other equation is going to force z upon me. I won't have a choice. Once I've determined what x and y are, this equation will determine what z is. So let me write that general strategy down. That's a good general strategy for these parameterization problems when you have two intersecting surfaces. Now, it doesn't always necessarily work this way. Sometimes it can get a little bit more complicated, and maybe we'll see that in the future, but this is going to work here. So in particular, I'll start out by considering this ellipse-looking equation, which, if I were to parameterize this, I would turn it into a bit more of a standard form by dividing through by 4. And I'll do a bunch of algebra in one step, but if I divide both sides by 4 here, I would get x squared over 4, which I could write like x over 2 quantity squared, plus, here, when I take 2y squared divided by 4, I'll get y squared over 2, which is the same thing as y over root 2 quantity squared, and that equals 1. Okay, then I think about my favorite trig identity of all time, which is cosine squared plus sine squared equals 1. This guy right here dictates what I want to call cosine and sine. I want this to be cosine squared plus sine squared. So this tells me that I want to let x be, well, I'll call x over 2 cosine of t, which means x can be 2 cosine t. Likewise, this tells me that I want to call y over root 2 sine of t, which means y should be root 2 times sine of t. Now, this is what I was talking about. We used one equation to determine what our x equation and y equation is, but now we don't have a choice. We know that this curve of intersection here has to satisfy this other equation. So whatever we call z, it has to be 1 plus x squared minus y cubed. Well, we've already determined what we're going to call x and y. So again, we don't have a choice. Z has to be 1 plus 2 cosine t squared minus root 2 sine t cubed. So let me write that out, and then we're done. There's our z function, and then if we want, we could write this in vector form, and then we've successfully parameterized this curve. So to conclude, I can say that our parameterization, r of t, is going to be a vector. It has 3 components, because this is a curve in 3 dimensions. The x component up here is 2 cosine t. The y component is root 2 sine t. And then the z component is right here, which was forced upon us by this other equation. So z is going to be 1 plus 4 cosine squared t. Whoops, this should be a minus. Sorry about that. Minus 2 to the 3 halves sine cubed of t. And there you go, we're done. Like I mentioned, this is a good example of a problem where, on the one hand, we can try to draw a picture, and usually it's never a bad idea to do that, but you don't want to just rely on geometric intuition. At some point, you just have to trust the equations and go from there. And we could have arrived at this parameterization without drawing this picture, and really without even thinking at all about what these surfaces look like and what this curve looks like. Anyway, so there's a good delicate balance between relying on pictures, using geometry, and just trusting the equations. And this is going to come up a lot throughout the course.